respects this rule. And now I'm very happy to and proud to introduce Robert's keynote. Dr. Robert Hilbrich works as a manager for simulation and modeling at the German Aerospace Center in Berlin. He's a computer scientist and started his research career in the field of developing safety-critical real-time systems at Fraunhofer Research Institutes. Since 2015, Robert has been responsible for the development of the traffic simulation suite Eclipse SUMO project, and he will certainly talk about that during his presentation. So Robert will present today the importance of open simulators and AI in changing modeling landscape. So dear Robert, the floor is yours as soon as I will stop sharing my screen.
Thank you, Philippe. Thank you for the invitation. I'll try to share my screen. I hope it works.
It does.
Perfect. Then welcome everybody, and a warm welcome from me and a good morning. I don't have to say anything more regarding myself, I guess. So let's skip over the part about myself. Let's talk briefly about the German Aerospace Center. It sounds like a research organization just for aerospace. In fact, we do also do research in traffic and mobility. And I'm part of the branch that is doing research in this area. It's a pretty large research organization. Now I think we have about 10,000 employees in Germany, so it's pretty significant. And my institute that I'm working at is based in Berlin, and the other half is based in Brunswick. And of course, we do research in real-world mobility. For me, coming from a computer science background, this field proved to be very special, probably because it had to do with the real world. Because here, you can't easily get your hands on data for the full situation that you have. Usually, when you do experiments in computer science, you just have like the data for everything you want to look at, right? But here, it's really hard to understand where, for instance, all the vehicles in a city are. It's hard to know where do people want to go to. And once you design something really cool, like a traffic management strategy, it's really hard to do this, because how do you tell everyone, like the next morning, to change their typical route? And if you want to compare the effectiveness of your strategy, you can't just do it the other day in a similar pattern just to make sure that you did it right. So doing something in research that has an effect on the real world is really hard. And this is really something that I learned during the last years. And this will also be like, let's say, the governing title or the governing theme of my presentation today. Of course, we at the DLR, we look at several ways to make the mobility systems and cities better. They could become more green, they could become smart, user-friendly. And of course, it's not only trying to make the cities, let's say, more friendly for automated vehicles. You have to look at the humans that are actually living there. So you have to look at city planning, you have to look at traffic planning, you have to look what do people actually do. And once you get to the people, it's really starting to get complicated, especially for computer scientists that are usually trying to work with deterministic machines, right? And in order to do our research there, in order to address these issues here, we developed SUMO, which is a traffic simulator. You can compare this as a kind of miniature trains. Like you usually look from like in a 2D perspective from on top of it, and then you can really see the vehicles moving and the persons moving and everyone moving. And we use it to build a digital twin of a city. And here, I don't want to dwell too long on SUMO, because usually you can have a look at the website. There are several talks about it. you might just recognize the Sumo logo on top, and you'll see it a couple of times today, where I try to make sure that you see that there is some Sumo inside. So Sumo, I guess, will be one of the themes you'll see more often today. But today, the real focus of my talk is I would like to look at the intersection of mobility and artificial intelligence, because this is one of the key themes for this conference. And well, when you look at trends, like when you look at Google Trends, for instance, here what I tried to do is I asked Google, well, let's look at the search terms for reinforcement learning, for artificial intelligence, and for autonomous driving. Well, you can basically see that if you take autonomous driving as a proxy to how far has AI been adopted in the mobility world, you can see that apparently, at least according to Google Trends, it is lagging behind. AI in general and reinforcement learning, they somehow supersede the success of autonomous driving. And the question that I want to talk about in this presentation is, well, why is that? Do the researchers in the mobility domain, don't they have any interest in AI? Is it that? Or is it just very simple that they don't need to search for autonomous driving? Well, and in order to address this question, we'll start off by looking at some of the success stories, and later on at some of the challenges that AI has to face when it comes or when it needs to be put into the world of mobility. And maybe these challenges will explain why these trends are the way the Google Trend Analysis is presenting it to us. So brace yourself, but we're going to ease in with some of the typical success stories. All right, let's talk about success. Everyone wants to hear about successful stories, right? This is one of the typical ones, right? You have seen these or images like this at least a million times when you're in this area. So when you talk about AI in mobility, the first thing that comes to mind is usually image recognition and vehicle classification. And it does indeed work really well. We also do this at the DLR, and I think this is the area where AI really shines. And to be honest, some people even refer to the capabilities of AI as being superhuman. It may have exceeded the capabilities of humans when being able to classify vehicles on a road. All right, easy enough. And to be completely honest, it's not hard. It's really not hard. You can do it yourself. You can do it quickly. You can see one of our Dell laptops that we got at the DLR. Next to it, you can see a Raspberry Pi with a tiny camera. So there's a readily available software stack that you can use to do image recognition in your office. And it's really not hard. You can see the apples and the Coke bottle that it recognized really quickly. And it's nice. So it's not really hard. It's not totally rocket science. You can do that. And there are a lot of tools available to help you do that. All right, so this is really easy. But let's look a little bit more deeper. Are there any other use cases where you can apply AI in the mobility world? Well, here's another one. It's called Flow. Flow is a deep reinforcement learning framework from the UC Berkeley. And what you can basically do here is you can try to see how AI may help to improve the traffic situation in cities. You can basically test out if vehicles were controlled by an artificial intelligence, then you would have the ability to optimize for certain behavior. And of course, in order to do this, as you might have guessed from the logo on the top right, there's also Sumo included as a microsimulation library. And there's a really neat video that I would recommend you to watch. It shows how a controller based on AI has learned with the help of deep learning to drive in such a way that traffic congestion is mitigated. There have been a lot of research papers afterwards to discuss this in greater length. And there are discussions about whether this is actually feasible in reality. But nevertheless, it's showing a glimpse into what's possible, right? And it's really well done. So I would really recommend you to have a look at this video. We don't have time in this keynote to do this, but the slides are going to be available afterwards. And I would really recommend you to have a look at it afterwards. Okay. The success stories sound pretty good so far, so let's move on. What do we have here? Well, some people say accidents in the mobility are really bad. Shouldn't we do something with the AI about it? And they started off with trying to estimate the probability for an accident, trying to do this even live based on the current traffic data and combining it with past accident data. The data that they took here, and you can see the link to the paper on the bottom right, they took a Chinese highway about 200 kilometers length. They tried to get their hands on the traffic data. It's not easy, as I mentioned at the beginning. And they added the accidents from 1 month, from April 2014. This were about, I think, 1,300 accidents that occurred in this month. And then they split the April in 1 minute time intervals and labeled each one with a label called accident and the other ones with no accident. And they tried to learn a classifier based on this data. And the result was pretty convincing, not really good. About 60% of the crashes could be identified before they were happening. I'm not sure how long before, but they could be identified. The problem here is that, well, accidents are really rare. So what you do is you learn an imbalance in the data. In Germany, at least, accidents happen only about every 280,000 kilometers for each vehicle. That's pretty rare. You have way more time intervals of 1 minute length where you don't have any accident than you have a time interval with an accident. So in essence, the deep neural network essentially learns, well, it's a better choice for me to learn no accident. And this is a problem for researchers, especially when you have really rare events. But to be honest, even if we had a perfect model, the question, I think, would be rather, well, what would you do with a perfect model? What do you actually tell the drivers? Ooh, there's an accident coming up. Try to focus more? Do you tell them to brake quickly? How do you make sure that the message that you would convey to the drivers, how do you make sure that this message is actually being well communicated in such a way that you don't cause any other accidents while doing that? And if you have a lot of false positives because you prevented accidents, would people still continue to listen to you? So the question sometimes, what I'm trying to get here is, the question is really not only to have the perfect model, but when you try to bridge the gap to the reality, it is really important to think about the consequences and how would people actually perceive the recommendations that you generated. And this is really hard. This is really hard to work with reality. And this brings us neatly to the difficulties of using AI in the real world. So after addressing the success stories, let's take a deeper look at the challenges. Well, one of the challenges, like everything in life, is training, because training is really hard. You need a lot of data. And if you're doing some research in machine learning, you've probably stumbled upon a lot of research and articles about the quality of data and a potential hidden bias in this data. Of course, you usually have data that captures past events and object encounters. This is not easy, and we'll get to this back later. And sometimes even you don't have enough data, so you enhance your data pool with synthetic data that you can get from a simulation. And there are a lot of people that are using SUMO to get traffic data, because as I stated at the beginning, getting traffic data, how vehicles move from the real world, is really hard. So the question immediately arises, do you trust the simulator? Is it really mimicking the important aspects of the reality? It's not hard, but you need to address these questions. And then you really start your training and you really plow through the data sets, and you'll probably use a lot of computation power. Or in some cases, you will probably even go to the big data sets and to the big AWS, what you get there, right? And when your data changes, when your experiment changes, you're going to possibly retrain the network again. And suddenly, it might occur to you that the carbon footprint and the discussion about it is really starting to kick in, because it does indeed take a lot of effort and a lot of energy to really train your network. And finally, you'll also need to think about the objective function. Usually what you do, right, is you need to give the AI a goal to train for, which we call an objective function. Usually this function is about to be minimized. Well, in the small world of a computer scientist, and I can say that because I am one of this crowd, this sounds easy. It's usually just a function with a set of variables that you want to minimize. However, the reality is way more complex. And you will gonna have a really hard time to include all of the relevant variables in your objective function. And if you do, well, you still need to make sure that it's somehow tractable to minimize. And we'll see examples later on of where the objective function is not complete and what you get if you're not paying attention here. All right, let's continue with one of the challenges. Here you can see the results of another research project at an intersection in Utah, in the United States. What they did here, they tried to adopt deep learning algorithms, of course, to get the best possible traffic light control strategy at an intersection. And of course, they also used SUMO, as you can see on the picture in the middle. The results are on the right-hand side. And you can see the delay that is caused by the vehicles due to the traffic control strategy. A higher delay is bad, and a smaller delay is obviously better. And on the bottom, you can see the episodes that they used for training, and each episode is essentially a full day of traffic for training. Okay, and what you can see here, that some of the algorithms, oh no, I forgot to mention, the current strategy is the actuated one, the blue one. The other ones are different varieties of deep learning strategies to learn. And what you can see here is essentially the AI strategies could become a little bit better compared to the current one, but not terribly better. They're only better after about 20 days of training. And the interesting thing here is the code is available online, so you can do it yourself. You can test it out yourself and do it on your own machine. And of course, we did this. And the results are essentially, we spent only about 1 day of computing time. So we started our laptops, we downloaded the code, we started with SUMO and said, okay, 1 day, give me the best you have. And after 1 day of computation, we only managed to get through 12 episodes for just one algorithm. And when you look at the graph, then you can see that with 12 episodes, it depends on the algorithm that you pick, you only get about as good as the current strategy. So what I'm saying here is that your mileage may vary, and you can play around it with your own computer and your own computing equipment. Next up, it's not only the other students that are doing this, we are also doing that, and we are also doing a similar project with traffic lights in Hamburg. And the goal of us was to develop a custom AI-based traffic light control strategy. And of course, we also did reinforcement learning with SUMO, and our optimization function was essentially try to minimize the time loss for all vehicles. And these are our results. Once again, the first 4 control strategies are non-AI. And the last one, AI, is the new one that we tried to learn with deep reinforcement learning. And you can see that it's actually not even the best one. It's not even the best one. It was a little bit better than average, but not by a lot. And we mentioned the optimization function before, and we learned the hard way. What did we learn? Well, the solutions that we produced generated too long of a cycle time, meaning when you almost made it to a green light, how long does it take for you to get another green light? And the generated cycle time by the deep learning algorithm was simply too long. It didn't correspond to the expectation of the real world users. So essentially, our optimization function was incomplete. Once again, pay attention to the variables that you put in there. Next up, challenge. Another challenge was, well, when you look at AI after you pass training, it's a little bit of a black box. You don't have any explicit knowledge of what it learned. It's just implicit knowledge. It does something, and honestly, there's no way of really knowing what it will do. And if there's no way of what you can know or what you can like understand of what it will do, well, I think there are essentially 2 ways of dealing with it. And there's an interesting blog post from a couple of years ago where people say, well, this high-dimensional data space that the AI learned and optimized, our brains are possibly not able to really comprehend these spaces. So now we have two options, essentially. One option is we just leave it to the computers and say, okay, we just assume that there are some things that we as human beings cannot do, like we cannot see ultraviolet light, we cannot smell certain smells. Maybe these are just certain things that our brains are not fit to understand. Or we work on how to be able to understand these things. And this is hard. This is really hard. And in some areas, you might say, okay, this is not a problem because I don't need to really understand. But in some areas, you do need to understand. And safety critical systems, you do need to understand how and why something is happening at all points in that time. And the current approach that we have here, right, is an approach of total observation. So we try to see what this thing does for any given input and any given time, essentially. And this is one aspect where simulation is happening, where people are using SUMO for. And at Eclipse, we have a working group called the Open Genesis Working Group, where we try to address these topics as well. And at the DLR, we also created, or we founded, a new institute that is focusing on challenges like this, trying to understand how do we understand what's AI doing and how can we make assurances about its behavior. And of course, we're researchers, right? So we want to know if if there is explicit knowledge that we have and implicit knowledge that is learned by the AI, we were curious if knowing the white box or if knowing about what's happening does indeed lead to a better result at the end. So here's an interesting challenge. It started off by the ACM, the Special Interest Group in Knowledge Discovery and Data Mining. And well, you are here in charge of coordinating the traffic signals to maximize the number of vehicles served in a city while maintaining an acceptable delay. So what they have essentially here is a virtual city, and you can influence all of the traffic lights. And the goal is really to optimize your traffic. And of course, they used SUMO in the backend. Well, this is great, right? Circling back to the optimization function, they want to optimize the average of the travel time divided by the free flow travel time, meaning the time that you took due to your traffic control strategy, with respect to the travel time that you took if there were no other cars and no traffic lights at all. So essentially, they were trying to get a feel for the additional delay that is caused due to your traffic. But look at the formula really closely. There are trips with different length. There are trips where they're only a minute long, really short trips, and trips for vehicles which are about 30 minutes long. And if you have a 10-second delay at a traffic light, this does indeed affect the vehicles with shorter routes more significantly, because a 10-second delay, if you only have a 1-minute trip, it's really bad. If you have a 30-minute trip, 10 seconds, well, that's not much. So what did we do? Well, of course, we took also part and we tried to optimize for vehicles with shorter trips. This might be a side effect of where we actually learn something about an incomplete optimization function. Is this really intended for reality, you might ask? Well, I'm not sure. To be honest, we didn't do really bad. There were about 1,000 teams, and the SUMO team passed the qualification round on 8th place. I think we even made it to 7th, and now we're in the full round, and I think it's going to be really interesting to see if we guys, knowing like a lot about traffic and SUMO, if we are able to beat what the AI is able to do. All right. Sometimes changes happen. I guess you've all heard it, right? And sometimes these changes are not easily reflected in the data that you're using. And these unforeseen things are happening. And here I just picked out some of the numbers of 2020. We don't have the figures for 2021 yet. Just to give you a feel for what's really happening. And they're really significant changes. I don't want to like read them now, and please excuse me that the right-hand graphics is in German. It's one of the original graphics. It's basically telling you that there's a higher drop in flight traffic. Road traffic is affected as well, the red line, but it's not really bad. And the blue line is railroad traffic that has been affected, but not as much as the flight traffic. You can look all these numbers up. It's really significant. And how does your AI, based on data, how does it look at these things and predict these things? And will there possibly be a long-term effect? Will people suddenly have realized that working from home is great, and will they move to suburbs? Well, it's not clear yet, and it's really hard to predict this with historical data. Sometimes there are also new technologies that affect your mobility system. Here are some of these effects, and they really have an effect on properties, on key properties, like costs, like comfort, and how people actually use this. And mid to long term, Germany has about 49 million cars. Have we reached peak car yet? Will there be some significant initiative that is somewhat regulating cars, even some more? This will have a significant effect on how people actually move. And even now, we have a very heterogeneous mix of active mobility, micro-mobility, different kind of scooters that are driving around. People, or the choice of mobility, it has become more personalized. And it's really hard to get an understanding with when you only have data of the past. So what can you do if AI is tricky? Well, you can try to use open data to facilitate a collaborative data management, working together with multiple stakeholders. And of course, you basically also need to combine it with simulation and modeling, because this improves your understanding and this improves your ability on what to predict. I hear you say real-time data is really hard to get, especially open real-time data. Well, let's look at the next slide. And well, of course, as I stated at the beginning, you need to enhance your system with modeling and simulation. It is hard, I know, but it's key to understand, to be able to predict and to work with a changing reality. Quick one, real-time data. We're using Telegram now. We're starting a major campaign in Berlin. And here you can just get a Raspberry Pi with a small camera. You can just plug it onto your window, and then you get traffic counts for pedestrians, for bicycles, for cars, for heavy vehicles, and you get it real time, and it's open for everyone. There's a public API to get this. So these tools are available. So coming to an end, some things to take away for you. Well, the reality is really complex, and your mileage when you apply AI may vary. Please don't underestimate the resources that you need for its training, because there's a lot of, well, we need to look at the climate, right? And there's a significant carbon footprint. Also pay attention to the optimization function. It's usually incomplete, and you only feel it when you try to adopt it into the real world. And of course, modeling and simulation might be old school, but these are still tremendously valuable tools that should be at your disposal to really make use of your ideas and to make them transferable to reality, essentially. All right, thank you so much. I think I took a couple of minutes more, but I think we should be fine. Thank you very much. I'm open for questions.
Thanks a lot, Robert, for this very interesting presentation.
Pleasure.
Do we have any question? I didn't see any of them, at least on the chat. Do we have any question? So maybe I will launch a question in this case. I actually have a couple of questions for you. First of all, you were talking about AI as well. So I would like to know why people do not use simulation more often, but rather seems to prefer a black box think like AI for such use cases.
Usually, thank you for this question. Usually some people think that it's really hard to get started with simulation. And we try to reduce the burden of trying to come up with a simulation scenario by providing tools that help you do that. We still recognize that building a scenario, like a digital twin of a city, is hard work, and we usually say it's something about about 6 months to a year that you can easily spend on trying to get this perfect. So we recognize that this is really hard, and not everyone is an expert in this field or wants to become an expert in this field, right? And AI comes with this promise of, oh, there's a black box, I can just start this algorithm, I can just start this code, and then it's fine. It promises to be more simple. And we recognized that that's what the reality is. And so we started off with a spin-off company where we tried to build a mobility simulation as a service. As you don't want to, let's say, really get into the nitty-gritty details of building a sumo simulation, sometimes it would be more valuable for folks to get their hands on a running simulation as a service. And maybe this way we can lower the barrier of people to adopt this kind of technology and make use of the power that it gives you. Yeah, maybe this, yeah.
Thank you for it.
Oh, pleasure.
You have a comment, at least on the chat, thing that's very interesting summary on AI and traffic. So I would like to ask you another question. I had the chance to travel once to Brasilia in Brazil, and actually the city has been designed by architect Oscar Niemeyer to avoid any intersections, at least at the beginning, and preferring bridges to crossroad because his wife actually died in a car accident. So can we imagine that in the near future, urban architect will create city inspired by such simulations?
They should, absolutely should. The thing is, simulations are usually the last step when you try to do something, right? You have a very fixed infrastructure and you have some kind of traffic demand, or where do people actually want to start and go to? And well, I think the key part is most of the cities in Germany, at least, are centered around the cars. The car-friendly city was one of the key concepts from, I think, from the 1920s, where everyone tried to make sure that the cars were able to move around. And this concept has really been ingrained in German cities. And we need to make a really strong look at it again, at this concept, if this is really feasible for the foreseeable future, if this is a really feasible concept for the cities of tomorrow. And if we get to the idea that, well, maybe there are better options, I think Paris and Copenhagen are two of the famous examples of where they try to get away from the car-centric city. Even if we get to this point, it's really hard to just, well, rebuild our cities, right? Because you have to repurpose streets, you have to retrain the mentality of people. You have to make sure that all the things that the people do, the infrastructure that they need is reachable and that it's there. So what I'm saying here is it's a long process. It's a really long process to change, and simulation can help you to make this argument and to make people understand, hopefully, but it's a long process.
Thank you again. We have a question from Sartak. How about the data information exchange or interoperability of the digital model twins /twins in DLR system? Is it feasible or happening already?
The data exchange in the DLR systems and digital twins? Well, I think at the moment, the current state is that everyone is offering certain APIs. And we would be happy, or we're trying to offer APIs, as OpenStreetMap has their API, Telegram has its own API. There's a lot of people that are offering APIs. There's in Germany several initiatives offering mobility data. There's a lot happening, but really there's no real, let's say, standardization that is governing a lot of places, a lot of initiatives. So it's really hard to really, if you're doing something in your own city, you really need to see, okay, what's there? What data can I get? To be able to build the adapters to get your hands on the data that's there. There's no real perfect solution for everything. It's really the nitty-gritty details, trying to get your hands on reasonable data. But this is something that is very dynamic and changing environment, and a lot of people are trying to yeah, trying to make this better and to improve this. And I think open source and open data are one of the two key ideas that will help here to facilitate this.
Thank you. I will take just the last question because I don't want to consume too much on the break yesterday. It was maybe too short. Does the AI black box incorporate human behavior, human adaptation of new technology? From Mohammed.
I think I don't want I'm not an AI specialist. There are, of course, I bet there's like millions of papers trying to incorporate human behavior. But the key aspect of AI is that you are trying to learn something from a data set. And this data set may be flawed. This data set, of course, captures human behavior. Of course it does. And you're trying to adopt it, right? But what I tried to get at is the optimization function that you try to learn or minimize. That might be flawed as well. And the data source that you do might capture human behavior, but only parts of it. Because some people are simply not a part of your data set, or it covers only parts of the day, or people in other areas behave differently. What I'm trying to say is that the world is more complex than the mind of the computer scientist would hope to, or would hope for. And trying to go to the reality saying, oh, I got this perfect model, well, it is challenging and probably doomed to fail.
Great. So thanks again, Robert, for this very inspiring presentation. And so now we will have a